Welcome to the glass plate. In this example, we're going to take a look at the effect of external resistance to heat transfer for a very basic case. The case is as follows. We have a flat plate with area capital A and thickness D, in which heat is produced in a uniform way. That means that the heat production per unit of time and per unit of volume, Q with 3 dashes, is a constant. Given is that the plate is very wide compared to with thickness D, so that it basically has no ends. We will ignore the ends. Furthermore, and for this exercise very important, the resistance to heat is external. That states that the internal heat resistance can be neglected. The outside has an ambient temperature T infinity, meaning that the temperature away from the surface is given as this constant. And the questions are, what do we now know about the internal temperature of this plate at steady state, and can you compute it? The first question is what you know about it. And that calls for global understanding. So I'm going to write in that in principle there is also an internal resistance or a transfer coefficient H. And we know that the internal resistance 1 over the transfer coefficient compared to the external resistance is negligible. So this is much smaller, or H internal is much larger than H external. Now if we use the analogy with Ohm's law, it in a steady state means that there must be a temperature jump from here to here. The temperature jump is kind of our driving potential, the delta V if you do it in Ohm's law. Thus from an Ohm's law perspective, let me use blue, that is slightly better to see, I would have drawn something like this. Here is the potential difference, the driving force, delta V, the temperature difference here, and that sees two resistances in series. And thus a current will be flowing, and there is an internal resistance and an external resistance. And there will be a potential drop from here to here and from here back to the battery or whatever it is. Now that it is given that this one is 0 compared to that one, Ohm's law tells you that there is a current flowing, but there is no resistance, so the I times R internal is 0, and thus the potential drop from here to there is next to 0. All drop in potential, the voltage, is over the external one. Translate it back. That means that there is no significant driving temperature difference from the internal of the plate towards the plate wall, the end. This is this point. And all jump is located here. This is going to be the delta T, and there is delta T next to 0 internally. Rephrased, this plate is at a uniform temperature. There's hardly any gradient, hardly any distribution. That is very handy, because if I need to compute now the temperature of this plate, or even the average temperature of the plate, I can call this temperature Tp, and it is uniform everywhere. And if I need to compute it, I set up an energy or a heat balance over the entire plate. And in steady state, that reads as 0 equals what is flowing in, nothing, minus what is flowing out. Well, there is heat flowing out in a steady state, because by the heat production this is heating up. So area times Newton's cooling law, H external, because the internal doesn't matter, there's no resistance there, times the driving force, which is the temperature of the plate, minus the temperature far away, that's T infinity. Oh, but I shouldn't forget that the plate has two sides. So also here, heat is going out and that is just the 2 here. And obviously there's heat production, so in the entire plate, the production per unit volume times the total volume is what is produced. And from this, it is rather trivial to back out the temperature of the plate. That's going to be the temperature far away plus Q triple times D over 2 H external, the area A dropping out. And this is the solution. But notice that I heavily rely on that the plate has only a single temperature. That's sufficient to quantify the temperature of the plate, thanks to the reasoning here. Try this yourself. Good luck.